Hey everyone, in this video I would like to take a look at the different types of discontinuity. We have three main types that we use, and what I want to do is just start off by taking a look at what these discontinuities look like. So the three main ones are removable, jump, and infinite discontinuity. Let's start with removable. So just to sketch this out, a removable discontinuity is a function that is pretty much continuous except at a specific point where we have a hole. So let's say that this is the number c. This is continuous everywhere except when we get to c, that point is missing. And maybe that point is somewhere else. So maybe it's up above our graph, or maybe it's undefined at that point. But the graph is continuous everywhere except at that specific point. So in this case, if we look at the limit as x approaches c of our function, this limit does exist. However, the limit is not the same as the function value. So the limit as x approaches c of f of x, this is not equal to that function value at c. Okay, the second type of discontinuity is a jump discontinuity. And in this case, we have a break. Our function jumps from one value to another. So maybe we're moving along, and then here at c, maybe my function stops, and then it jumps up to another value, and then continues on. So we're jumping from one value to the next. Looking at the limits in this case, our two one-sided limits are different. So the limit as x approaches c from the left is not equal to the limit as we approach from the right. So looking at the picture, these two y values, these are different. So the limit as I approach from the left is going to approach this first one, so maybe that's y1. But the limit as I approach from the right is approaching the second one, maybe that's y2. So our last type of discontinuity is infinite discontinuity. What this one means is that as our limits approach this value of c, our limits are actually approaching positive or negative infinity. So for example, maybe my function looks like this. So as I approach from the left, as I get closer to c, maybe my function shoots way up and it keeps going up to positive infinity. On the other side, as I approach from the right, maybe it shoots down and it goes towards negative infinity. If I look at the limits on this one, so for this case, the limit as x approaches c from the left, this one is going to be equal to positive infinity. And then the limit as I approach from the right is going to be equal to negative infinity. So as I get closer and closer to that value of c, my function is either getting closer and closer to positive or negative infinity. Hence the name infinite discontinuity. So now we know what these look like. Let's use them in an example. So here I have a function, and what I'd like to do is I want to figure out if this function is continuous at a couple values for c, and I want to know if it's discontinuous, what type of discontinuity do we have. So this piecewise function is broken up into 4 parts, and let's start by graphing this. So I'm just going to work my way from left to right. So let's start with this very top piece. So this one is defined for all the values of x that are less than 0. So starting at the y-axis, x is 0, and then working my way to the left. So 2/3 x plus 2, this is just a line. It has a y-intercept of 2. I do have to be careful here because at 0, I don't have the or equal to part, so I'm going to put an open circle at 2. And then this line is going to go to the left. So I'm just going to use my slope to graph a couple more points. So Okay, that takes care of the first part. Now the second one, we have at exactly 0, we have the value of 5. So in our function, at 0 and 5, we have this one specific point. On the other side of 0, we're going to start up with the third one, which is an absolute value function. So the absolute value of x minus 2. And this is going to be for everything from 0 and then all the way up to and equal to 4. Now this absolute value function, we do have a transformation there. The x minus 2 just moves everything to the right 2 spots. So the vertex is going to be at the point 2, 0. And then absolute value, we have a slope of positive 1 going to the right. And then at 4, we do have the or equal to, so that's going to be a closed point. And then we have a slope of negative 1 going to the left. And then here, I do have another open circle because we don't have the or equal to part. And then connecting those together, we'll get our absolute value graph. And then lastly, our very bottom one there is a parabola x minus 5 squared. And this is for all the values that are greater than 4. So x minus 5 squared, again, we have a transformation where that minus 5, that just moves everything to the right 5 spots. So the vertex of my parabola is over at 5, 0. From here, if I wanted to pick out a couple values to plug in, I could. Or just following the pattern of perfect squares, I can plot a couple more points for our parabola. So I go over 1, up 1. If I go over 2, 2 squared, I go up 1, 2, 3, 4. And I think that's enough to give me a good idea. Going the other way, same pattern. And then here I am going to have an open circle because we don't have the or equal to. And then here's our parabola. Okay, so now that we have our graph, we can examine to see whether or not we have any discontinuities at these two values of c. Let's start with the first one of c is equal to 0. So as we move along our graph, if this was to be continuous, we should be able to keep going without having to pick up our pencil. But as I can see, as I get closer to 0, I do have a hole here. The function value at 0 is up here at 5, so that point is removed. So that means we have a removable discontinuity. If I examine these limits, so the limit as x approaches 0 from the left of our function, I can see that this is equal to 2. The limit as x approaches 0 from the right of our function, this is also equal to 2, but our function value g of 0, this is equal to 5. So our limit is equal to 2, but our function value is equal to 5. So because those are different, that means we have a removable discontinuity. Okay, let's take a look at the second one, and let's see what's happening at the value of 4. So at x equals 4, on the graph is right here. And as we move along our graph, we can see that our function is jumping from one value down to the next one. So that means we have a jump discontinuity, but we can justify that looking at the one-sided limits. So let's take a look at the limit as x approaches 4 from the left. And as I'm coming from the left, I'm following along this absolute value piece. My y values are approaching 2. So the limit here is equal to 2. Now if I look at the limit as I come from the other side, so as I approach from 4 from the right, in this case I'm following along the parabola, and as I get closer and closer to 4, my y values look like they're approaching 1. So because these two one-sided limits are different, that means we have a jump discontinuity at 4.